In case one, we had the advantage of having the structural information of the protein and ligand in order to guide the design. But what if we don't? That's exactly what we're going to be tackling in this second use case. How can we design novel molecules without access to the 3D structural information? In this case, we are starting with just the ligand information, non-protein structure. Our reference ligand is a known PIM1 inhibitor. We are using a fragment-based approach again, but this time with two exit vectors, which give us more room to explore in both directions from the central scaffold. Using the fragment growing generator in MACHIA, we introduce diversity on both sides of the molecule. From the chemical constraints, we define two exit vectors on the molecules. These are the points from which MACHIA will grow. You set them manually based on what regions you want to explore. Then we layer in substructure filters, in this case using SMARTs to exclude unwanted features. Next, we apply the descriptors-based constraint. We limit here the molecular weight to 500. Finally, MACHIA uses its internal datasets of commercial building blocks and named reactions to propose only synthesizable molecules. Now that we define our chemical constraints, the next step is to add a reward to guide the generators toward the kind of molecules we want. And since we do not have a protein structure in this case, we are using ligand-based 3D similarity. There are 2 points we are combining here. On the left, we have a 3D pharmacophore fingerprint. This encodes the spatial arrangement of key features like hydrogen bond donors, acceptors, hydrophobic contacts, based entirely on the reference ligand. The AI is rewarded when new molecules maintain a similar interaction profile. On the right, we use 3D shape similarity. This captures the overall volume and conformation of the reference ligand. So we are encouraging MACHIA to generate molecules that occupy similar space and preserve shape-based complementarity, even in the absence of protein. Together, these rewards help us bias the generation towards ligands similar to the reference one without needing a 3D target structure. Let's now demonstrate how to set up the 3D ligand-based rewards and the generator in the MACHIA platform. Let's begin by accessing the 3D ligand-based module. Here, we can create a new 3D ligand-based settings. The primary input required is the SMILES or the SDF of your reference molecules. If you don't have the 3D conformation of your molecules, no worries. By inputting the SMILES, MACHIA will generate up to 100 conformations. You can select the one that best represents your needs. Here, there is a very important consideration. It's defining the anchor. This anchor must be a substructure of your reference ligand and should be present in all generated molecules. It is the common point between the reference and generated molecules, allowing MACHIA to compute the 3D shape and pharmacophore with respect to your reference ligand. Without an anchor in both the reference and generated molecules, MACHIA can't optimize your molecules. Once you decide to input your SMILES and your anchor, then you proceed to get the conformers. Here, MACHIA will generate up to 100 conformers and will display them 10 by 10. You can select the one that best represents your needs. Once you select the conformation that you want, you press Saved, and your 3D ligand-based settings are ready to be used. With the 3D ligand settings in place, we move to the generator module. Here, we'll first define the exit vectors with two starting points of growth, a bromine atom and a carboxylic acid. Given that we need at least 2 steps to grow this fragment, we'll set the generation steps between 2 and 4. In the product constraints, we introduce two physical-chemical descriptors, a maximum molecular weight of 500 and a QED of at least zero point 0.3. We also utilize a list of SMARTS patterns in order to avoid unwanted substructures. This way, Macchia will generate molecules and will filter out all those with the unwanted substructures. Next, we need to connect the 3D ligand base to the generator so Macchia understands that it has to optimize the shape and pharmacophore as reward during generation. To do this, we return to the 3D ligand base module and select the desired one from the list of all the settings. Now we can generate molecules and observe Macchia's result. In all cases, the molecules are grown starting from the heterocyclic core, introducing diversity around it. Clicking on See Details allows us to view the initial fragment and the building blocks Macchia predicted to react with it to yield the final molecule. We have access to various scores such as 3D pharmacophore similarity and 3D shape similarity and the R score, a measure of the synthesizability of your molecule. Finally, you can visualize the 3D shape and compare it to your reference ligand in order to assess the alignment and overall similarity.